speaker is Professor Murad Alim from Harvard University, Edinburgh. The title of his talk is From Gromov Witten to Donaldson Thomas Invariants Where Resurgence.
Okay, thank you. So let me start by saying that it's a great honor to be part of this very special occasion and to be able to give this presentation here. So let me start by saying, so I was a postdoc in Professor Yao's group at Harvard Math Department from 2012 to 2015. But in some sense, I became a member of the Yao family a bit earlier, and it's deeply connected to the center that we're celebrating today. So my PhD work was in mathematical physics on the physics side and was very related to work that Professor Yao had done on topological string theory and also on mirror symmetry. Then I was a postdoc in the physics department at Harvard, and in 2011 I had my first discussion with Professor Yao. And we've all heard this morning, so Professor Yao is a brilliant mathematician, of course, but also a very good recruiter. So in the middle of our scientific discussion, he asked me a question that maybe a lot of people in this room have heard from him at some point, namely, what is your job situation? And that was the opening line from him to ask me whether I'll be interested to join his group after my physics appointment. So I was very honored and glad about this. But then eventually my physics appointment came to an end. And I didn't know how to get back to this conversation because Professor Yao at the time had been here at Tsinghua building the center. So I decided to just send my whole application credentials to Professor Yao, including reference letters and everything. And then I got an email back, not mentioning the application at all, but Professor Yao asked me to come here and teach a course on my research. And at the time, I thought this is sort of an extended interview, so I accepted. And I came here and was very glad. So that was the beginning of a very fruitful collaboration interaction. So I'm very grateful for the impact that Professor Yao had on my own research, on my career, on my personal life. And I'm also very grateful for Professor Yao's work on bringing together mathematics and physics. And this is also going to be the subject of my talk. So it's very related to things that I had worked on with Professor Yao and also previously. And it's about, so the title is From Gromov Witten to Donaldson Thomas invariants. So it's not going to be related to definitions of these invariants in enumerative geometry, but rather about ideas how these invariants are organized in generating series. And sort of the punchline of the talk is that Gromov Witten invariants, as we have seen in the previous talk in particular, higher genus Gromov Witten invariants are organized in a certain series, and the series is asymptotic, so it doesn't have any radius of convergence. And the main question is there still some analytic functions behind this series, which makes sense? And the answer is yes, but there's not generically not just one, but there's many different possible ways. And these are labeled by Donaldson Thomas invariants. So in the path to go from one to the other, in my talk is going to be a resurgence. So this is based on some work that I have been doing for the last few years, as well as some work in progress, and work with collaborators. Lotte Holland, who is also at Herford University, Arpan Saha, who's in Hamburg, Jörg Teschner, also in Hamburg, and Ivan Tully, who used to be in Hamburg and is now in Sheffield. So let me start by motivating. So it's really about the motivation for this line of research is that so wonderful things are happening at the intersection of mathematics and physics, really pushing the boundaries of both disciplines. The particular type of interaction that I have in mind is really around the geometry of quantum field theory and string theories, and in particular, the very fruitful idea that in physics has had a lot of impact, namely that physical theories should not be considered as isolated objects, but rather should be thought of as members of some family. So all the parameters, coupling constants, masses that go into the definition of a physical theory should not be thought of as fixed, as would typically be the case in physics. But all these parameters should be thought of as varying and actually as being some local coordinates on a space of theories, which often has the interpretation as a moduli space. So this idea was pivotal in the work of Seiberg and Witten, where moduli space of vacua of a certain four-dimensional n equals 2 theory was identified with a moduli space of complex structures of some elliptic curves. And all of a sudden, many physical computations which weren't possible previously were possible. But also the interaction goes the other way around. So we've seen in the previous talks that for some reason, mathematical invariants that can be defined purely mathematically are very efficiently packaged in terms of physical data. So often, if you're interested in mathematical invariants, a useful thing to look at them is generating series of all invariants. And these often have interpretation in terms of partition functions, physical partition functions. Also, the two types of invariants, which are going to be very important in my talk, are the Gromov Witten type invariants and Donaldson Thomas type invariants. So also there is a mathematical counterpart of physical ideas and physical problems. Namely, in physics, there's typically a perturbative formulation. So this is related to Gromov Witten invariants. Namely, you just genus by genus of Riemann surfaces, you look how you can map into some target space. But there's also some non-perturbative way of thinking about invariants. Namely, you just fix your target space, which in my talk is going to be a Calabi-Yau threefold. And then you start giving enumerative meaning to interesting subspaces there. And there are some invariants associated to that as well. Then, as we've also seen in Celi's talk, often out of surprisingly nowhere, the generating functions turn out to be themselves have an interpretation in terms of some quantum mechanical problems. So this is also going to feature in my talk. Okay, so maybe let me just set the stage. And we've, in the last two talks, heard a lot about mirror symmetry, but maybe let's just recap the story. So mirror symmetry originated as the statement that there is two 10-dimensional string theories. One of them is called type 2A theory. The other one is called type 2B theory. String theory can be thought of as a theory of maps from the strings or the string world sheets, so two-dimensional Riemann surfaces, into a 10-dimensional space. And the 10-dimensional space is typically taken to be a product of a complex Calabi-Yau threefold times R4. And mirror symmetry is the statement that if two different string theories are taken on a mirror pair of Calabi-Yau threefolds, then what obtains are identical four-dimensional theories. Moreover, the power of mirror symmetry really not only comes from the fact that there is this isomorphism, but really that there's isomorphism comes in families. And the fact that the families on the two sides are very different. So on the one side, which in my talk I'll refer to as the B side, so this is also consistent with Bong-Yan's talk. On the B side, the moduli space of the Calabi-Yau is the moduli space of complex structures. On the A side, the moduli space is the moduli space of complexified Kähler forms. And more than a matching of moduli spaces, there is a matching of vector bundles, complex vector bundles, together with a flat connection. So also this was mentioned in the previous talks. So there is a system of variation of Hodge structure which is matched on both sides, which triggered a lot of interest in mathematics, because out of the data of this flat connection, there was in one go the generating function of all genus 0 Gromov Witten invariants. But the story goes further. So there is also higher genus mirror symmetry. And this is captured by topological string theory. So topological string theory, for the purpose of my talk, is just going to be, you should think of this topological string theory associates a partition function called this Z top to a given family of Calabi-Yau threefolds. So there's, again, the two sides, A and B. And the topological string partition functions associated to both sides are expected to be isomorphic if one is able to find the right coordinates, local coordinates on the moduli space. And the crucial feature of this topological string partition function, the way it's defined physically, as also was mentioned in the last talk by BCUV, for example, there's a recursive structure. And it turns out that as a power series in this formal variable lambda, which is the topological string coupling, it is as an asymptotic series. So it has zero radius of convergence. So it doesn't make mathematical nor physical sense, strictly speaking. So, and this is one question we're going to address in this talk. So as I mentioned before, so topological string theory encodes the generating series of higher genus Gromov Witten invariants. So the topological string free energy in a certain limit becomes the Gromov Witten potential. So this is organized again as an asymptotic series in this topological string coupling. And then the generating functions of the Gromov Witten invariants at genus G with curved class beta. So gamma would be the lattice, the second homology lattice of the given Calabi-Yau threefold. And here Q are also thought of as some formal variables. So the Gromov Witten potential can further be split so into a piece which comes from constant maps, which has a very universal structure, and a piece which comes from non-constant maps. So this is the one containing the interesting Gromov Witten invariants. What was found by Gopakumar and Wafa is that there is a slightly better way of organizing the Gromov Witten invariants, which at the same time also gives us hope that it's not just an asymptotic formal power series at lambda, but maybe in terms of as a function of lambda, it has some honest meaning. And that's the Gopakumar-Wafa resummation. And the conjecture is that these Ng beta are sums of Gromov Witten invariants with certain weights, which are integer. And at the same time, the asymptotic series in lambda becomes some meromorphic, or can have the interpretation as a meromorphic function in lambda. So here you see from the -2 has infinitely many poles on the real axis. But this is something that we're going to address in this talk, whether this is already some candidate for an analytic structure in lambda beyond just the asymptotic series. So let me also mention the homological mirror symmetry, which featured in Bong Yan's talk. So this was the homological mirror symmetry conjecture formulated by Kunsevich, that the bounded derived category of coherent sheaves associated to a Calabi-Yau X should be isomorphic to the derived category, Fukaya category of the mirror manifold Y. So this has been proven in many cases by now, but what you may ask is, and part of my motivation, I mentioned that considering Calabi-Yau manifolds and theories in terms of families was a very powerful idea. So what happened to the moduli space M here? So here, this conjecture, or the homological mirror symmetry, is typically just for particular Calabi-Yau and its mirror. And where does the moduli space come in? So here's again where the interaction with physics was very important. Namely, the statement is that one is not generically in physics interested in all the objects in these two categories, but only, strictly speaking, in subcategories, namely subcategories of stable objects. So there is a notion of stability, which again is choosing, so what the stability is doing is choosing a special set of objects. And the special set of objects are physically called the BPS objects. So that's a Bogomolny-Prasad-Sommerfeld. And that's generically in physical theories. There's a bound on the mass of an object from below, given by the absolute value of something called the central charge. And the objects that saturate this bound are called BPS objects. And this can be translated into a stability condition and can be translated in the two categories to the fact that in the Fukaya category, one is strictly speaking only interested in special Lagrangians. And in the category of coherent sheaves, one is interested in stable coherent sheaves. And the right stability condition was formulated by Douglas, Fjoll, and Römelsberger. Namely, that's the stability condition using the physical central charge, which is again a linear combination of the periods. But this stability condition was abstracted mathematically by Tom Bridgend, not restricting to this physical slice of the moduli space. And then the statement of mirror symmetry would be that object by object, you can match stable sheaves with special Lagrangian, and you can associate invariants to these special objects, and these are called the Donaldson Thomas invariants. And then if you can organize these invariants in terms of some generating function, then the expectation would be that the physical generating function of BPS states would correspond to the generating function of Donaldson Thomas invariants. And then, of course, you can ask, what is the relation between the generating functions of stable objects and the generating function of Gromov Witten invariants? And this is also goes way back. So there is works of Maulik, Nekrasov, Okunkov, and Pandaripanda conjecturing that for certain class of Calabi-Yau manifolds, the two are the same if one does some appropriate changes of variables. And the physical counterpart is the Oguri-Sturminger-Waffa conjecture, saying that the Z BPS in a particular instance becomes a Z of a black hole that should be related to the topological string partition function. My talk is going to be about more recent progress, namely, so there has been a few years ago work of Tom Bridgeland, following work of Gaito, Moore, and Latsky, really starting from the categorical part and formulating a Riemann-Hilbert problem whose input data is all the DT invariants of a triangulated category and their wall-crossing structure. And out of this data, formulating a Riemann-Hilbert problem. And what Tom Bridgeland showed in particular examples is that once this Riemann-Hilbert problem is solved, it also contains the all genus Gromov Witten theory. My talk is going to be about the reverse direction. So whether if one starts with all genus mirror symmetry, whether one also has some data of Donaldson Thomas invariants or BPS states. And the answer is going to be yes, but qualitatively, the approach is very different from above. Okay, so the basic question is whether the topological string partition function or this generating function of Gromov Witten invariants has any meaning beyond being just an asymptotic series. So in physics terms, this means, is there any non-perturbative completion of this topological string theory? And this is the question that has been addressed over many decades, exploiting lots of wonderful dualities of topological string theory with many other branches of mathematical physics. So, for example, matrix models, Trent-Simons theory, and so on and so forth. The problem, well, not the problem, is most of these dualities are just for a restricted set of Calabi-Yau manifolds and using results from other branches. So the basic question is there any intrinsic way of addressing this question, or is there any way of really understanding what is the analytic structure in lambda of this generating series? And this is something that actually we had addressed with Professor Yao and Jay Zhao back when I was a postdoc. Namely, we were asking, is it possible, like you would have at genus 0, for example, the variation of hot structure problem completely determines all degree at genus 0. Is it possible to derive some differential equation in lambda for this object? And we were able to derive some area equation, but in a particular limit. So this was already a hint that there is some geometric meaning in lambda. After being a postdoc at Professor Yao's group, so I kept returning to this question every couple of years until eventually I was able, in a particular instance, to find such a differential equation, which really governs everything. And it turned out to be a differential equation, but a finite difference equation. So that's one set of ideas of not resorting to any other dualities. The other set of ideas is using the methods of resurgence. So this is growing interactions between math and physics, and really things that have been formulated very rigorously on the math side of how to deal with asymptotic series and how to address their analytic structure. So the particular example that I'm going to talk about is, you should think of this as a building block, and actually a work in progress that I won't be able to talk about is really showing that this is a building block and it's enough to understand this example. And that's called the conifold singularity. So the conifold singularity is this singularity in C4, where x1 to x4 are complex coordinates. It can be deformed by just replacing the 0 with a complex number on the right-hand side. And it can also be resolved by replacing the origin with a P1. So for the small resolution, this gives a non-compact Calabi-Yau threefold, which is known as the resolved conifold, which is the total space of the rank 2 bundle over the projective line. And for this, Gopal-Kumar and Waffa, using duality with large N, Trent-Simons theory, were able to write down the full genus generating function of Gromov Witten invariants, and it was also checked by Faber and Pandey-Panda that this is the correct thing. So this is a fully explicit series, and by knowing the growth of these Bernoulli numbers, it is also known that this series is asymptotic. So this is a very explicit case where everything is known, but it's still a bad series in lambda. The Cooper-Komura-Baffa resummation, so if you look at all of this, for the resolved conifold becomes very simple. There is essentially only one non-vanishing Cooper-Komura-Baffa invariant, and that's the one in front of this coefficient here. So what I was able to do, since the full series is known, so if there is some equation in lambda that governs this series, then it should be possible to derive it from there. And this is something that I was able to do, adapting techniques of these people. I was able to find a finite difference equation, shifting the moduli by finite amounts of the topological string coupling. And on the right-hand side, there was only genus 0 result. Okay, so this is, we already knew, so if we didn't know the full answer, then this would completely determine the asymptotic series. But since we already knew the asymptotic series, what good is another way of asking the question? So what good is knowing this finite difference equation? Well, the answer is if you're able to find also an analytic solution of the finite difference equation, then this is a good candidate for the analytic structure in lambda of your series. And indeed, I was able to find an analytic function. So this is one particular integral representation. So this is related to what is called the triple sign function, which also solves this finite difference equation. So I thought, okay, this is then the non-perturbative completion, or this is the analytic function behind topological string theory. And indeed, if one repackages the content of this function, then one obtains part of it is the Cooper-Komura-Baffa resummation. And then there's infinitely many corrections, and all of these are suppressed in lambda. So if you look at asymptotic series of all of this in lambda, then all of this is 0. So this is not visible in the asymptotic expansion. However, when I talked to colleagues in Hamburg about this, in particular Jörg Teschner had the expectation that there shouldn't be just one non-perturbative answer, but there should be many. So together we addressed the problem using techniques of resurgence, which I want to go through just very quickly. So resurgence is telling you if you have an asymptotic series, so here near 0, so a particular reason for series to be asymptotic if the nth coefficient of this power series grows factorially. So you can immediately show that this is divergent. So what you do then is look at the Borel transform. The Borel transform is obtained by taking the original series and just explicitly dividing the nth coefficient by n-1 factorial and introducing a new variable. And then you go to look at the Laplace transform. This is called the Borel sum. This will have exactly the same asymptotic expansion as the original series, but it will have a whole half space where it is analytic. So to appreciate this, just let us quickly go through an example. So if your asymptotic series was on the nose, just growing factorially, meaning the nth coefficient is n factorial, then the Borel transform is the following. So the coefficient, if you divide this by n-1 factorial, is just 1. And you recognize here the geometric series. So as a power series, the radius of convergence is 1. But then you can analytically continue this by recognizing that it's also the power series expansion of this course of this meromorphic function. And then the analytic function behind this is the integral representation where you do the inverse Laplace transform of this Borel transform. So it's given by this expression here. And then the basic question is, if your Borel transform, so here it's a meromorphic function, it has a pole at 1. So what's the difference between defining these Borel sums in along different ways in the Borel plane? Well, the answer is simple. So the difference between these two is just given by the residue of this meromorphic function. And you see here in this very simple example, the difference is suppressed in Z. So if you expand this again as a power series in near 0, then it gives 0. So both of these analytic functions are the same up to this factor here. And for topological string theory, the answer is very similar. So that's a theorem with Arpan Saha, Jörg Teschner, Ivan Tully. So this is the full Borel transform for the topological string theory on the resolved conifold. The important thing to take away is just the pole structure here. So we have simple and double poles, and there are infinitely many. So they occur for integer m and integer k. And the picture is the following. So there is infinitely many poles along infinitely many rays, which accumulate along the imaginary axis from above and below. And in order to define some analytic function, which is the Borel sum, you need to avoid these poles. And this is also something that we did. And you can also ask the question, what is the difference between the analytic functions that you obtain by avoiding the poles in two different ways? And this is something that is known as the Stokes jumps. So this is something that we could compute from taking the residues of the explicit expression along all the poles, and it had nice compact expressions. And in particular, we found that there is some distinguished Borel transform along the real axis. And this recovers the special function, which I had found earlier as a solution to the difference equation. And then using the Stokes jumps all the way up to the imaginary axis, what we're also able to do is to show that there is a limiting Borel transform, which is nothing but the original Kupper-Kummer-Waffer resummation. So the general picture is, and this is something that we also proved by matching our work with of Tom Bridgend, is that the coefficients of these Stokes jumps are nothing but the Donaldson Thomas invariants of the underlying same Calabi-Yau threefold. And the interpretation of this, moreover, so either you say, well, what's behind Gromov Witten theory is a piecewise analytic function, or you can say it's actually a section of a line bundle, and all these Stokes jumps are just giving the transition functions of this line bundle. Moreover, that's something interesting. Once you have the analytic structure in lambda, then you can just go back to the original asymptotic expansion, but you can also decide to look at the expansion in 1 over lambda. And the surprise is that 1 over lambda it also has an asymptotic expansion. And we don't know yet what the normative geometry meaning of this is. So it looks very related to Gromov Witten theory, but of both closed and open strings. And another natural question. So, sorry, in the dual variable, so in 1 over lambda, there's also a whole resurgence story with its own Stokes jumps, and it relates to many other interesting mathematical problems. And furthermore, the analytic function satisfies another difference equation. So this difference equation is telling you that the analytic function in lambda is no longer periodic in T, but rather it has some violation of this periodicity, and the violation is precisely the Stokes jumps of the weakly coupled expansion. So another other aspects of this work is sometimes these finite difference equations can be interpreted as some quantization of a curve. Also, this can be done in this case. So there is a way of packaging the topological string partition function such that the difference equation can be written as a quantization of a curve. And this is related to what is called quantum Picard-Fuchs equations. Also, this is a very nice story, which wants to be generalized further more. Moreover, this is also work in progress. Now that you have some geometric meaning of the topological string coupling, you can also ask, is there more modular structure? And it seems that the answer is yes, but it's not modular of some very straightforward kind. It turns out to be related to modularity studied by Felder and Barchenko, namely the elliptic gamma function. So let me maybe stop here and just summarize. So what I discussed is how Donaldson Thomas invariants can be extracted from analytic structure behind Gromov Witten theory. The physics behind this is really the relation between perturbative and non-perturbative expansion. And so mathematically, this can be addressed using Borel resummation or trying to find differential or difference equations which govern this expansion. So let me stop here. Thank you for your attention, and wish Professor Yau a happy birthday, and also the center a happy birthday.
Yeah. Any question, comments?
Couple of I want to understand. So one is DT, your DT invariants, that the coefficients that appear there are which sheaf invariants are these? What's that sheaf?
So In the talk that I gave, so these are also for the resolved conifolds. So these are sheaves supported on P1 as well as point-like sheaves. So in physics
Point-like sheaves.
will be D2, D0 invariants.
But then in the Gromov Witten DT invariant story, these sheaves are supported on all of the variety. They are 6-dimensional support.
Yes, what is the question?
Well, your sheaves are your sheaves supported on P1 or on the whole Calabi-Yau?
There are two different appearances of DT invariants. So one of them is the weak coupling expansion. So there's the Gromov Witten theory near lambda equals 0. So there the coefficients are related to DT invariants that are only supported on P1 and as well as point-like objects. But then what I mentioned at the end is there are also the dual expansion. So at 1 over lambda, so when 1 over lambda is close to 0, there you have DT invariants, and these are the D6, so one
D6
one
branch
D6
arches.
and D2, D0.
So these are ideal sheaves. Another question, using this, can you make yet another guess for what the GV invariants are associated to? Like I think sheaf theoretic definition of objects where the Gopakumar-Vafa invariance associated to is still actually is problematic. So there is work of Malik and Toda, and there was work of Sheldon Katz. So can you tell what the GV invariants are in terms of sheaves?
Sorry, so again, so the talk is not about the definitions
No, I know,
of the
but-
invariants or the
but
content of
can
the
you
invariants. It's
extract
rather
it?
about how the invariants are organized.
Yeah.
And it's rather about, so it's like the similar question at genus 0 would be asking, okay, there is one thing defining Gromov Witten invariants for genus 0 curve. And the other thing is understanding that this can be obtained from a flat connection. So the talk is rather in the spirit of trying to understand how the things are organized and what's the
Okay,
what's
so
the
there's
idea.
make
So
no
it's not
predictions
the
about GV.
invariants themselves.
Okay, good, thanks.
If there are no questions, that's it. Yeah.
I would like to remind people that there's a typo in the paper version of the handbook. So from 5:30 to 6:30, we have the special lecture by Professor Wu Rongli. And after that, we will have dinner.